Hello, everyone, and welcome to the 10th lecture of AAE 301. In this lecture, we will look at an alternative way to describe a system, which is known as the state space representation or state space model. And as always, let's kick off with an overview of the lecture. First, we will start with an introduction to the state space models. Then, we will look at how to obtain a state space model for a system described by a linear constant coefficient ODE or LCC ODE. We will also cover how to derive the transfer function of a system from its state space model. Finally, we will delve into the solution of a state space model as well as a key component in the solution called the matrix exponential. Okay, now let's get into the details. First, the state space model is a representation of the dynamics of a system described by an nth order differential equation with n initial conditions as a first order differential equation in an n vector called the state with an initial state. Typically, the state space model is comprised of two components: the state dynamics of the system, which is a function of the state x of t, the input u of t, and time t, and the output equation, which is also a function of the state, the input, and time. The state dynamics indicates how the system state evolves with its current value, input, and time. The output equation indicates how the output measurement is related to the system state, input, and time. Here, I'd like to elaborate on the state. The state is a set of variables called state variables that completely describe the current condition or configuration of a system at a particular time. In other words, all past states and input history are summarized by the current state. Moreover, if we know the input and the current state, then we can determine the future behavior of the system. To help you understand better, let's look at the unit mass system as an example. For this system, the state variables can be chosen as the position x of t and velocity v of t of the mass. From the governing equations of the system, we can see that these two physical quantities, x of t and v of t, completely describe the condition of the system at time t. In other words, it summarizes all past states and input history up to the time t. In addition, if we know the position and velocity of the mass at time t and the input force starting from time t, then we can determine the behavior of the mass at any time after t. Now, before I move on to the next example, I'd like to share some advantages of a state space model over a transfer function. First, the state space model takes the initial state or initial conditions of a system into account, while the transfer function does not. Second, the solution of a state space model, namely the state x of t and output y of t associated with initial state x of 0 and input ut, can be solved by numerical integration, which can be done efficiently by computers. On the other hand, obtaining the output y of t associated with the input u of t from the transfer function requires operations like partial fraction and Laplace transform, which are time-consuming to compute. Third, transfer functions are limited to linear time invariant systems, while state space models are applicable to even nonlinear or time-variant systems. Fourth, the input u of t and output y of t of a state space model can be vectors. This makes a state space model a more suitable alternative to describe a multi-input, multi-output, or MIMO system. Lastly, the state variables and the state dynamics allow us to gain more insights on the system, including the internal stability, controllability, and observability of the system. These properties play an important role in designing a controller and state estimator for the system. And you can learn more about these properties in AAE 564. Now, let's see how we can obtain a state space model for a system described by a differential equation through an example. In this example, we focus on the mass spring damper system. Here, the input, which is the horizontal force exerting on the mass, is denoted by U of t, and the output, which is the horizontal displacement from the wall, is denoted by Y of t. The equation of motion of the system is a second-order differential equation given by m double dot equals to u minus c times y dot minus k times y. In addition, the initial displacement and the initial velocity of the mass are y naught and y dot naught. Now, let's derive the state space model from the differential equation. Step 1, we need to define the state. Since this is a second-order system, we need to define two state variables. And just like the unit mass system, the state of the mass spring damper system can be described by two physical quantities, the horizontal displacement and velocity. Here, we define the state variable x1 as the displacement y, the state variable x2 as the velocity y dot. And the state x is a vector of x1 and x2. And according to our definition, the initial state of the system x of 0 is a vector of y naught and y dot naught. Step 2, we need to specify the state dynamics. In other words, we need to express the time derivative of the state in terms of the state x, input u, and time t. Recall that x is a vector of the state variables x1 and x2, and that x1 represents the horizontal displacement y, and x2 represents the horizontal velocity y dot. Therefore, we can see that x dot is equal to a vector of y dot and y double dot. Now, notice that y double dot is not a state variable, but from the equation of motion of the system, m double dot equals to u minus c times y dot minus k times y. We know that y double dot is equal to 1 over m times u minus c times y dot minus k times y. Next, recall again that the state variables x1 is equal to y and x2 is equal to y dot. So we get x dot equals to a vector of x2 and 1 over m times u minus c times x2 minus k times x1. Now we have obtained an expression for the time derivative of the state x dot in terms of the state x and input u. Notice that we don't see time t in the expression because this system is time invariant. And since this system is a linear system, we can further rewrite the expression in a matrix vector form as x dot equals to ax plus bu by defining two matrices A and B. Step 3, we need to specify the output equation. In this example, the output measurement is the horizontal displacement of the mass y. Now let's express the output y in terms of the state x, input u, and time t. Recall that the state variable x1 is equal to y, so here we can express the output as y equals to x1, or equivalently x1 plus 0 times u. Similar to the state dynamics, since this system is time invariant, we won't see the time t in the output equation. Moreover, since the system is linear, we can further rewrite the output equation in a matrix vector form as y equals to cx plus du by defining two matrices C and D. Okay, now we have derived a state space model of the mass spring damper system, and the state dynamics of the system is in the form of x dot equals to ax plus bu. The output equation is in the form of y equals to cx plus du. And the initial state, and ABCD matrices are summarized here. In the state space model of the mass spring damper system, which is an linear time invariant system, we see that the state dynamics can be expressed in the form of x dot equals to ax plus bu, and the output equation can be expressed in the form of y equals to cx plus du. In fact, this applies to all linear time invariant systems. Therefore, we can specify the state space model of a linear time invariant system in terms of the matrices A, B, C, D. Now let's take a closer look at each element in the state space model of a linear time invariant system. Here, X is an n vector that denotes the state of the system. Y is an m vector that denotes the output of the system. U is a p vector that denotes the input or control of the system. And here, matrices A, B, C, D are called the system matrices. Specifically, A is an n by n matrix that is called the state transition matrix. B is an n by p matrix that is called the input matrix. C is an n by n matrix that is called the output or sensor matrix. And D is an n by p matrix that is called the feed-through matrix. In addition, the state space model can also be described by a block diagram shown here. This block diagram can be divided into two parts. One part in green that is related to the state dynamics, and the other part in blue that is related to the output equation. To help you better understand the diagram, let's focus on the part related to the system dynamics first. The system dynamics is described by the equation x dot equals to ax plus bu. We know that the integration of x dot is x, so the output of the integrator with x dot as an input is x. We also know that x dot is equals to ax plus bu, so the summation of ax and bu is equal to x dot. Next, let's look at the part related to the output equation. The output equation is described by the equation y equals to cx plus du. So the summation of cx and du is equal to y. Okay, this is the end of the introduction to the state space models. Now let's move on to the next section, the conversion between representations of a linear time invariant system. Let's start with the conversion from an LCC ODE to a state space model. Specifically, we will look at an nth order LCC ODE with n initial conditions. Here, y is the output and u is the input. Let's start with the conversion from an LCC ODE to a state space model. Specifically, we will look at an nth order LCC ODE with n initial conditions. And here, y is the output and u is the input. Also, notice that there is no time derivatives of the input u in this LCC ODE. Now, let's convert the LCC ODE into a state space model. Step 1, we need to define the state variables. Since this is an nth order LCC ODE, we need to define n state variables. Here we define the state variables x1 as y, x2 as y dot, x3 as y double dot, all the way to xn as the n minus 1 derivative of y. And we let the state x to be a vector of x1, x2, all the way to xn. With our definition of the state, the initial state x of 0 is a vector of y of 0, y dot of 0, all the way to yn minus 1 of 0. Step 2, we need to specify the state dynamics. To derive the state dynamics, we look at the first time derivative of the state x dot. Recall that the state variable xi is defined as the I minus 1 time derivative of y. Therefore, we can see that x dot is equal to a vector of y dot, y double dot, all the way to the nth derivative of y. Now, notice that the nth derivative of y is not a state variable. But from the LCC ODE, we know that the nth derivative of y can be expressed in terms of the state variables and the input u as bu minus an minus 1 times yn minus 1 all the way to a1 times y dot minus a0 times y. Next, recall the definition of the state variables. We can replace y and its time derivatives with the state variables. Then, by introducing the state transition matrix A and the input matrix B shown here, we can further rewrite everything in a matrix vector form. Here, the matrix A is an n by n matrix consisting of three things: n minus 1 by 1 zero vector, n minus 1 by n minus 1 identity matrix, and a 1 by n vector A consisting of all the coefficients of the LCC ODE. On the other hand, the B matrix is a n by 1 vector with all elements as 0 except for the element in the last row as B. Step 3, we need to specify the output equation. According to the definition of the state variables, we know that the output y is equal to x1, or equivalently x1 plus 0 times u. Similarly, by introducing the output matrix C and the direct transmission matrix D, we can rewrite everything in a matrix vector form. Here, the C matrix is a 1 by n vector with all elements as 0 except for the element in the first column as 1. As for the D matrix, it's simply 0. In summary, to obtain a state space model for a linear time invariant system described by a LCC ODE, we just need to pay attention to the order and the coefficients of the ODE and fill the corresponding values into the templates for the system matrices A, B, C, D. Now let's practice what we have learned with an example. In this example, we will look at a linear time invariant system described by a fourth order LCC ODE with 4 initial conditions and derive a state space model for the system. In other words, we will derive the system matrices A, B, C, D along with the initial state of the state space model for the system. First, since this is a fourth order LCC ODE, we know that the number of state variables we need to define is equal to 4, and this implies that the state is a 4x1 vector. Here, the state is a vector of y dot, y double dot, and y triple dot. And according to the given initial conditions, the initial state x of 0 is a vector of 1, 0, 0, and 0. Next, let's look at a general fourth order LCC ODE. By comparing the coefficients, we see that the vector A in the state transition matrix is equal to a vector of 8, 3, 4, and 2. The constant B in the input matrix is equal to 2. Then we can apply the result we have obtained previously to get the system matrices A, B, C, D for the state space model of the system shown here. Next, let's learn how we can derive the transfer function of a linear time invariant system from its state space model. Recall that the state space model of a linear time invariant system consists of the state dynamics in the form of x dot equals to ax plus bu, and the output equation in the form of y equals to cx plus du, along with the initial state x of 0. Now let's derive the transfer function of the system. Step 1. We need to apply Laplace transform to both sides of the state dynamics equation and the output equation. Recall that for a function g in the time domain, the Laplace transform of its time derivative is equal to s times g of s minus g of 0. Therefore, the Laplace transform of the state dynamics equation is s times x of s minus x of 0 equals to a times x of s plus b times u of s. On the other hand, the Laplace transform of the output equation is given by y of s equals to c times x of s plus d times u of s. Here, x of s is the Laplace transform of the state x, u of s is the Laplace transform of the input u, and y of s is the Laplace transform of the output y. Now, if we look closer at the Laplace transform of the state dynamics equation, we can derive that s times x of s minus a times x of s is equal to b times u of s plus x of 0. Or equivalently, xi minus a times x of s is equal to b times u of s plus x of 0. Then if we multiply the inverse of si minus a on both sides, we will get the inverse of si minus a times b times u of s plus the inverse of si minus a times x of 0. Then if we substitute this expression for x of s into the Laplace transform of the output equation, we will get y of s equals to c times the inverse of si minus a times b times u of s plus c times the inverse of si minus a times x of 0 plus d times u of s. Or equivalently, c times the inverse of si minus a times b plus d times u of s plus c times the inverse of si minus a times x of 0. Step 2. To obtain the transfer function, we ignore the initial state by setting it to 0, and then we get y of s equals to c times the inverse of si minus a times b plus d times u of s. Now recall that the transfer function g of s is the fraction of y of s over u of s. So we see that the transfer function g of s is equal to c times the inverse of si minus a times b plus d. So in summary, for a linear time invariant system described by a state space model represented by the system matrices A, B, C, D, its transfer function g of s is given by c times the inverse of si minus a times b plus d. Now let's practice what we've learned with an example. In this example, we derive the transfer function of a system described by the state space model with the system matrices A, B, C, D shown here. Recall that the transfer function g of s is equal to c times the inverse of si minus a times b plus d. Here, si minus a is equal to the matrix of s, 5, -1, and s plus 2. Next, recall that for any 2 by 2 matrix M, its inverse is equal to 1 over the determinant of M times the adjoint of M. Therefore, the inverse of Si minus A is given by 1 over the determinant of Si minus A times the adjoint of Si minus A, which equals to 1 over s squared plus 2s plus 5 times the matrix s plus 2, -5, 1, and s. We can now substitute this expression for the inverse of Si minus A back into the expression for g of s and get g of s equals to 4s plus 5 over s squared plus 2s plus 5. Okay, we've looked at how to obtain a state space model for an LTI system described by an LCC ODE, and how to obtain the transfer function of an LTI system described by a state space model. Now let's move on to the last section of this lecture, the solution to the state space model and the matrix exponential. First, let's recall again the state space model for a general linear time invariant system consists of the state dynamics equation x dot equals to ax plus bu and the output equation y equals to cx plus du along with the initial state x of 0. Here, we like to find the solution to the state space model, which is the corresponding state trajectory x of t and output trajectory y of t associated with the initial state x of 0 and input u of t. There are 2 steps to follow to obtain the solution. First, we need to solve for x of t by solving the ODE x dot equals to ax plus bu with initial state x of 0 and input u of t. Next, we need to substitute the solution x of t back into the output equation y equals to cx plus du to obtain y of t. Okay, now let's follow these steps to get the solution. First, we will apply Laplace transform to solve for x of t. Recall from the previous section that applying Laplace transform to the state dynamics equation gives us the Laplace transform of x, which is the inverse of si minus a times b times u of s plus the inverse of si minus a times x of 0, or equivalently, the inverse of si minus a times x of 0 plus the inverse of si minus a times b times u of s. Next, note that the Laplace transform of the matrix exponential e to the a times t is equal to the inverse of si minus a. Then we see that x of t, which is the inverse Laplace transform of x of s, is given by the product of the matrix exponential e to the a times t and x of 0, plus the convolution between the matrix exponential e to the a times t and b times u of t. Don't worry if you don't know what matrix exponential is at this point, because we will delve into it soon. Once we've obtained the state trajectory x of t, we can then substitute it into the output equation and get y of t equals to c times the matrix exponential e to the a times t times x of 0 plus the convolution between the matrix exponential e to the a times t and b times u of t plus d times u of t. or equivalently, c times the matrix exponential e to the a times t times x of 0 plus the integral shown here. Note that the impulse response of the system, which is the inverse Laplace transform of the transfer function g of s, is given by g of t equals to c times the matrix exponential e to the a times t times b plus d times the impulse function delta of t. Therefore, this term in the integral is actually g of t minus tau. Next, if you recall the definition of convolution, you'll realize that this integral is nothing but the convolution between the impulse response of the system g of t and the input u of t. So in the end, we see that the output y of t is equal to a sum of two terms, c times the matrix exponential e to the a times t times x of 0 plus the convolution between the impulse response of the system g of t and the input u of t. In the literature, the first term is called the zero input response because it is the output you will measure when the input is 0. The second term is called the zero state response because it is the output you will measure when the initial state is 0. So in summary, the solution to the state space model associated with initial state x of 0 and input u of t consists of the state trajectory x of t and output trajectory y of t. The state trajectory x of t is the sum of two terms, which are the matrix exponential e to the a times t times x of 0 and the convolution between the matrix exponential e to the a times t and b times u of t. Similarly, the output trajectory y of t is also a sum of two terms, which are the zero input response, c times the matrix exponential e to the a times t times x of 0, and the zero state response, which is the convolution between the impulse response of the system g of t and the input of the system u of t. Okay, we've seen that the matrix exponential plays an important role in the solution of a state space model, but we don't exactly know what it is. Now let's delve into the details and look at how it is defined and how we can compute it. First, let's recall that for any complex scalar a, the exponential function e to the at is defined as the power series shown here, which is the sum of the kth power of a times t over k factorial, and k is from 0 to infinity. The matrix exponential is defined in a similar fashion. Specifically, for an n by n square matrix, the matrix exponential is defined as the power series shown here, which is the sum of the kth power of a times t over k factorial, and k is from 0 to infinity. Here, the zeroth power of any square matrix is defined as the identity matrix. And note that, according to the definition, the matrix exponential e to the a times t is also an n by n matrix. In fact, you can think of the matrix exponential as a generalized version of the exponential function because the matrix exponential takes an n by n matrix as an argument, while the exponential function only takes a scalar as an argument. And due to the similarity between the definition of these two functions, they share several similar properties. The first property is the differential property. The time derivative of the exponential function e to the a times t is equal to a times e to the a times t. It turns out that the time derivative of the matrix exponential e to the a times t is also a times e to the a times t. Only that a here is a n by n matrix. And now let's derive this result together. Recall that the matrix exponential e to the a times t is defined as the power series shown here. So if we differentiate e to the a times t with respect to time, it is equivalent to the sum of the derivative of each term in the series. Here, the identity matrix, which is a constant, becomes 0. A times t becomes A. Squared of A times t over 2 factorial becomes A times t, and so on. Notice that the matrix A is in front of each term. So we can rewrite the sum as A times the series I plus A times t plus squared of A times t over 2 factorial, and so on. And note that the series here is exactly the matrix exponential e to the A times t. So in the end, we see that the derivative of e to the A times t is equal to A times e to the A times t. The second property is Laplace transform. Recall that the Laplace transform of the exponential function e to the A times t is 1 over s minus a, or the inverse of s times 1 minus a. It turns out that the Laplace transform of the matrix exponential e to the A times t is in the same form, which is the inverse of si minus a. Now let's see how we can get this result. First, let's assume that the Laplace transform of the matrix exponential e to the A times t is phi of s. Then recall that for a function g in the time domain, the Laplace transform of its derivative is equal to s times g of s minus g of 0. Therefore, the Laplace transform of the derivative of the matrix exponential e to the A times t is equal to s times phi of s minus e to the A times 0, or equivalently s times phi of s minus I. Also, note that the derivative of the matrix exponential e to the A times t is equal to A times e to the A times t. So the Laplace transform of the derivative of e to the A times t is equal to the Laplace transform of A times e to the A times t, which is equal to A times phi of s. From the Laplace transform of the derivative of the matrix exponential e to the A times t, we see that s times phi of s minus I is equal to A times phi of s. This implies that si minus a times phi of s is equal to I. Now, if we pre-multiply the inverse of si minus a on both sides, we see that phi of s, which is the Laplace transform of the matrix exponential e to the A times t, is equal to the inverse of si minus a. The third property is the solution to ODE. For the first order differential equation, x dot equals to ax with initial state x of 0, the solution is x of t equals to e to the at times x of 0. It turns out that for the systems of first order differential equations, x dot equals to a times x with initial state x of 0, the solution is in the same form, which is x of t equals to the matrix exponential e to the a times t times x of 0. Now let's prove this. First, we look at the derivative of x of t. We see that the derivative of x is equal to a times the matrix exponential e to the a times t times x of 0. Next, we look at a times x of t, and we see that it is equal to a times the matrix exponential e to the a times t times x of 0. Last, we look at x of 0. We see that it is equal to the initial state x of 0. Therefore, we can conclude that x of t equals to the matrix exponential e to the a times t times x of 0 is the solution to the systems of first order differential equations x dot equals to ax with initial state x of 0. Now let's learn how to compute the matrix exponential. In general, the matrix exponential is not computed according to the definition. Instead, it is computed using Laplace transform. And let's learn how to do this through an example. In this example, we will look at a system of first-order differential equations with initial state shown here and solve for its solution x of t equals to the matrix exponential e to the a times t times x of 0. Recall that e to the a times t is equal to the inverse Laplace transform of the inverse of si minus a. So to compute the matrix exponential, we first need to find the inverse of si minus a. Then we compute the inverse Laplace transform of it to get e to the a times t. And here, A is a matrix of 0, -1, 1, and 0. So Si minus A is given by the matrix S, 1, -1, and S. Next, recall that for any 2 by 2 matrix M, its inverse is computed as 1 over the determinant of M times the adjoint of M. Therefore, the inverse of Si minus A can be computed as 1 over the determinant of Si minus A times the adjoint of Si minus A, which is equal to the matrix S over S squared plus 1, -1 over S squared plus 1, 1 over S squared plus 1, and S over S squared plus 1. Now we compute the inverse Laplace transform of the inverse of Si minus A, and we get e to the a times t equals to the matrix cosine of t, negative sine of t, sine of t, and cosine of t. So in the end, we see that x of t is equal to the vector alpha times cosine of t minus beta times sine of t, and alpha times sine of t plus beta times cosine of t. From the example just now, we see that computing the matrix exponential can be quite time-consuming because we need to compute the inverse of a matrix and then compute the inverse Laplace transform of that matrix. This process becomes even more error-prone and time-consuming when the size of the matrix is large. Therefore, let's see how we can automate this process and compute the matrix exponential using the MATLAB command expm. To compute the matrix exponential e to a times t, we first define a symbolic variable t, and we define our matrix A, and matrix A is given by 0, 1, -1, 0. Now we use this command expm to compute the matrix exponential e to the a times t. And now let's run this and see what we get in the end. So the solution it gives us is a little bit messy because it did not simplify the expression. So here we will simplify the expression by using the simplify command. And now let's see what we will get in the end. So we see that in the end, we get this matrix, cosine of t, sine of t, negative sine of t, and cosine of t, which is exactly what we have obtained just now. Okay, this is the end of this lecture, and I will see you in the next one.